Now for some chessboards. These are basically little chessboards, varying size, not always 64 squares, but they'll be n by n, like in this case 5 by 5, since really they're just pictures of permutations. Especially when they ask you the question about the rooks. Rooks can travel in straight lines on the chessboard, vertical or horizontal straight lines. And so if you want 5 non-attacking rooks on a 5 by 5 chessboard, as 2A asks for, you have to put exactly 1 rook in each row and exactly 1 rook in each column. So that means a particular rook will be filling a row and a column. It'll fill the row that it's in and the column that it's in. Nobody else can be in the same row or column with that rook. And it's great if you are visual to just think about the picture that way. But the best way to solve the problem many times is to translate it back to permutations. So for this one, 2A, it says I'm not allowed to use the squares that are x'd out. So that means if I'm looking for permutations, I should think of this as a grid showing inputs and outputs. There's 5 inputs on the side, inputs over there. The outputs would be the columns. So here's the rook positioning, which would be allowed. An allowed rook positioning, let's say I put a rook here, and then let's say I have to be careful not to back myself into a corner, right? So I need, can't put it in this row anymore, but I could go with this row, and at least, in this row I can go with column 2. In this column I could use any of them, so I could be pretty free there. Here I have just either of these 2 left to fill in, so I'll try to go there. And now it might be a little bit of a chance to get stuck, but I think if I put one there in column 4, I'll have at least one option left in the last column down at the bottom. So the little circles there are my rooks, and the permutation is that 3 goes to 1, 1 goes to 3. So I could draw a picture of phi here, like we did before. 2, 3, 4, 5. 1, 2, 3, 4, 5. I'll label these dots carefully. 1, 2, 3, 4, 5. So the picture that I drew on the chessboard sends 1 to 3, sends 2 to 4, then 3 to 1, so back over to 1. 4 goes to 2, and I happen to send 5 to 5 on that one. Alright, so that in mind, what I'm trying to count actually is count permutations from 5 to 5, obeying some rules. The rules state that I can't use any of the x'd out squares. So that means phi of 1 does not equal 1. I can't use that square. And phi of 2 does not equal 2, 3, or 5. Just to list them in that fast way. Phi of 3 can't be 5. And phi of 4 can't be 3. Alright, so to finish the problem, I need to do inclusion exclusion. So I'll start with the total of 5 factorial ways to build those permutations. But then I'll subtract all the ways of breaking one rule, and I'll add back in all the ways of breaking 2 rules, and subtract all the ways of breaking 3 rules, and add all the ways of breaking 4 rules, and subtract all the ways of breaking 5 rules. And in fact, how many rules do I have? I have 1, 2, 3, 4, 5, 6. So I'll have to then ways of breaking 6 rules. There's 6 total rules. However, there's only 4 inputs, so that's going to cut down on the number of things that I have to count to when I'm doing those subtractions. So I'm not going to work all the way through this one. But there's 6 rules, and what would be nice to know is how many trees that I'll have to draw. So on the solution paper, you should try it yourself first, but then look at the solution paper. I have the trees drawn. But here's a way to know how many trees you expect to draw. So 6 rules, that'll be the portion where I subtract off the first thing I subtract off will be minus 6 rules times, and if you break 1 rule, there would be 4 factorials ways left to finish it. But numbers of trees are nice to know. So breaking 2 rules, I'll need trees for those. Two rules would be 4 choose 2 trees. So why are there 4 choose 2 trees? Because to pick 2 rules, I need to pick 2 out of the 4 inputs to break. There's only 4 inputs. You can write that down here as well. The 6 rules involve 4 different inputs. So there'll be 4 choose 2 trees to get 2 rules. Then for 3 rules, I'll have 4 choose 3 trees. I'll need to pick 3 of the inputs in order to break 3 rules. So this is the most. There'll be 6 trees for the 2 rule picture. Then there'll be 4 trees for the 3 rule picture. And then 4 rules. Well, that's just going to be 4 choose 4, which is just one tree. So for the 4 rules, I'll have to try to figure out if there's a way to break all 4 inputs, break a rule in all 4 inputs, and I'll get 1 tree for that. Now remember, when you draw the trees, then you have to worry about the one-to-oneness. You can't have a path on the trees that uses 2 outputs. But for now, I know I'm finished because there's no way to break 5 rules or 6 rules since there's only 4 inputs and I have to obey the rule that it's going to be a function. So there's 0 ways to break 5 or more, or you just cannot. I'll just say cannot break 5 or 6 rules. So when I get to that plus or minus portion, I'll have 0 for the 5 or the 6 rules that we break. Alright, so that's a good place to set this problem up for you, and then the rest of the solutions on the paper. So now I'll move on to problem 2b. Now, this is one where you could, in fact, do it the same way as 2a. Is again permutations from 5 to 5. But how many rules are there? Well, notice that every single x is a rule. So I'm not even going to try writing them out. Let me just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 rules. That's a bunch. And they do involve 1, 2, 3, 4 inputs. So they would have the same number of trees as this problem. Since they only involve, the rules only involve the 4 inputs, there's no rule for this row. They would involve the same numbers of trees. So strictly speaking, it's not totally impossible. But those trees are going to have a lot of branches. Because like when you get down to this rule here, or input 5, we call these the inputs. There's 1, 2, 3, 4 outputs that are outlawed. So there are going to be a lot of possible branches. It's not impossible. But I wanted to mention a shortcut. Okay, so first of all, the reason for the shortcut would be if you, or a heuristic for deciding that you might want to try the shortcut, is that you see so many rules to break that you think maybe those rules end up ruling out all but a few possibilities. So many rules implies a few possibilities. There's not many things that are allowed, and maybe you can count those easier. Well, this one turns out to be even faster than just counting the possibilities. So to try to count the possibilities, you might look at what's allowed in row 5. There's only one place that you're allowed to put a 0 in row 5. And then check out another row, like row number 1. There's only 2 places that you're allowed to put a 0 there, or place the non-attacking rook in row 1. And pretty soon, what happens is you try to draw a tree that would show all the actual possibilities. And in this example, you run into the fact that there are none. So let's just try that. So here's row 5, and there's only one possibility. Has to go in column 2. 1, 2, 3, 4, 5. Notice that you can start anywhere you want. I could start on row 4, but then I've got 5 possibilities right away, and or 5 options, which that would make the tree bigger than I want at first. So now let me go to row 1. Doesn't matter which order. Since I've already chosen 2 for row 5, though, actually there's only one possibility in row 1. Just put it there to show you, but on here, there's only one possibility left, which is be a 4. I can't use the 2 since I've already used it. This is exactly like drawing a tree to count the ways to break a rule, but this time I'm trying to obey the rule. Let's see, then for instance I could go to row 2. So row 2, now I've already used column 2 and column 4, so I've used column 4. That means for row 2 I only have one place left. It has to go here. It has to be in the 1 spot. And then now maybe I'll try row 3. Well, here's where I run into serious problems. In row 3, can't go there, can't go there, can't go there. It's sort of like playing a game of Sudoku or something. At some point, if you make the wrong choice, or if your Sudoku game isn't possible, you'll run out of options. So for row 3, all 3 columns have already been taken. So it's impossible to finish. And the answer to this one is 0. So sort of what I've done there is to count the few possibilities. This time the answer came out to 0. I could start drawing a tree that just shows which options I have for filling in the zeros. And if I had the possibility, then I would get to the end of all 5 of my zeros. So I ran out of options before 5 rooks. I keep calling them zeros, little O's for the rooks. Yeah. But if you didn't run out of options, you could get to the 5th rook and still be counting, and then you could count how many options you had on your tree. Now that brings up the question of what about trying that for this problem? Well, the problem here is that there aren't enough rules to make it completely viable, and as it turns out, it's on the borderline. If you work out the problem, check your answer with the key, it turns out that there comes out to 25 total possibilities. That's not impossible to draw a tree using this method. So go for it and see that you can do it both ways. It just takes a little bit more space than I'd want to use on a piece of paper for the tree that has 25 leaves at the end of it. And this method is very nice when the answer is any bigger than that, like that first problem where there was 240.